Yesterday we talked about the law of sines and how the law of sines will allow us to find distances in non-right triangles and find angle measurements in non-right triangles. Okay, so we said that if we had angle, side, and angle, side, angle, okay, essentially the makeup of two triangles where you have two known angles and a known side, okay, and however you configure them, they're going to be either angle, side, or angle, side, angle. That guarantees congruence, and that means that you're going to have one and only one solution. This picture right here is trying to demonstrate what we call the ambiguous case, okay? And when something is ambiguous, that means it can be left open to interpretation, okay? Means there's going to be maybe potentially different amounts of answers, okay? We're going to have a situation where there's no answer, okay? And I'll show you that one first here. The idea of what's going to happen here is the idea, and we can change the angles and change the distances here, and we will. But let's just say I gave you all a 45-degree angle cardboard cutout, okay? And then I gave you all two strings that one was 6.5 inches long and the other one was 3.4 inches long, okay? And I told you, using your cardboard cutout, okay, put that on your table, and then along one leg of your 45, put your 6.5-inch string down, okay, and tape it down to your desk. And then at the end of that segment, take your 3.4-inch string and configure it so that that 3.4-inch string will intersect the imaginary line that is defined by the other side of your cardboard cutout, right? Because I need to create a triangle here, so my cardboard angle has got that edge that I haven't attached any strings to yet, right? The idea before we know how long that side should be is that we let it be infinitely long, and then our third side, the 3.4, should cut that off somewhere, and that will establish how big my triangle is. Does that make sense, everybody? Okay. Let's give you an idea of what I mean by that. Right now, let's say instead of 3.4, because 3.4 is not going to touch down here, but this would be the scenario I'm asking you to do, okay? Don't worry about that segment there. Let's just get that one out of there. But this would be the imaginary line that's created by the second side of my cardboard cutout, right? I need to take this side here and rotate it to where it first intersects that imaginary line. And now, because it's intersecting an imaginary line, do I now have a triangle with those three components? Does that kind of make sense to everybody? Okay. Well, if I gave you a side length that was the 3.4, does that 3.4, no matter where I rotate it, does it touch this imaginary line to where I could close off my triangle? No. Okay. So that would be a situation where I can give you three pieces of information, an angle and two side lengths, and you might have no triangle that can be constructed, okay, because that third side length is ultimately too small, okay? And if you remember, I deleted a segment out of here a minute ago. And get it back. View. That segment right there, okay? If this is the imaginary third side, this segment here is perpendicular to that imaginary third side. That's the altitude, okay? So what has to happen is that this third side here has to be at least 4.6. Because if it's at least 4.6, then when I come down and swing down through here, it's going to touch that imaginary line right there, okay? And now I close it off and I get this triangle here, okay? Now, that would be a right triangle, correct? Okay? But if it's bigger than 4.6, say it's 8.1. Okay? If it's 8.1, then we can swing this and it'll touch there. And now it'll be an obtuse triangle, correct? Okay, this angle up here is most likely obtuse. Okay, but then does it ever intersect a second time? It does not. Okay, so we intersect only one time on that imaginary line, right? So 8.1. Okay, but here's where it gets a little bit tricky. Those would both be situations where we get one solution. Okay, so if I would give everybody a 45-degree angle cardboard cutout, a 6.5 segment, and an 8.1 segment, and said everybody create a triangle using that order of parts, angle side side, with 6.5 and 8.1 in that order, everybody would have the exact same triangle. Congruency exists with those values. Okay. What happens, though, that ends up being a problem is when I choose a number that is actually between these two for this third side. Okay, so just to make a point here, let's go back to that display there. I just want to make sure I'm zoomed in at the same level on both of these. Not. All right, there we are. All right, so if I choose, let's say we go to that side to be 8.5, and let's say this side here is 6.8. Okay. Let's come over here. I'm going to make the exact same triangle over here. Come on. 6.8 and 8.5. So 1, 2, 3, 1, 2, 3. All right. So right now I've got the same ordering apart, same construction, right? These two things are identical. So this is like you doing this and this your neighbor doing it. Okay. You might do this. You might construct this and say, okay, I'm going to make a triangle because Mr. Fay said I got to swing this to where it intersects that imaginary line, and we now get that triangle right there. Is everybody okay with that? Okay. But your neighbor might have missed that one. They say, well, I intersect that segment right there. And your neighbor gets that triangle. Okay. You still have the parts that were required. This is still this angle right here. Oh, it won't let me call that angle, but it's still it's this beta 1 here. It's still 45 degrees. This segment right here is still 8.5, and this segment right here is still 6.8, just like these two were, right? Are those two completely different triangles, though? That make sense? Okay. So if that were the situation, that's kind of getting back to what we talked about in chapter 4, that angle side side does not guarantee congruency. It can happen, but in general, all the time, it does not happen, because you might have a scenario like this. You might have angle side side components being 45, 8.5, and 6.8, but the two triangles are completely different. Does that make sense to everybody? So this would be a situation where you would go through the work, you would actually have two solutions that you have to report. Okay, you have to report the information about the triangle in the yellow, and you have to report the information about the triangle in the blue. Okay. Now the way that we do this is going to be pretty. It's as long as you stay organized, it's not bad. But I want you to understand why we do the step that we do. Okay. So I'm going to zoom in on this real quick, because the way I've got this set up, I really wasn't intersecting that side exactly. So I'm going to drag this down, and that's probably a better location. So let's go back to standard view there. And I'm going to do the same thing here. Zoom in, move that down. and then go back to standard view. All right. I want to look at these two angles. Okay, I want to look at this angle right here, which is going to be 62.11 degrees. And then we'll look at this angle right here, and it's 117.89. Can anybody tell me a relationship between those two angles? They're supplementary, okay? And that will be the case no matter what, okay? So what's going to happen when we go through the angle side to side, the ambiguous case, and the law of sines, because of the parts that they give us, the first proportion that we'll be able to set up will actually ask us to find this angle. Okay, that's the only way we can do this. Okay, the first thing we come up with the law of sines in the ambiguous case is an angle measurement. Okay, if there are multiple solutions, if there are two solutions, then the supplement of that angle will also be a solution. Okay, now the way that we are going to determine whether that supplement actually works and is providing a solution is that we want to make sure that, okay, so I knew that this was 45. This turned out to be 62 degrees, okay? Well, that leaves me enough room in terms of 180 degrees to have a third angle up here at A, right? Okay? When I look at that angle supplement, 62.11 supplement of 117.89, if I add 117.89 to the 45 that I know has to be there, do I have leftover room up here for a third angle? And I do. So that tells me that because there's leftover room for a third angle, I don't violate any other geometric properties, so there must be two solutions, okay? But let's say that, for instance, let's go to a scenario where we have something like this. So here you can kind of see that I would not intersect that line twice. So if I look at that angle right there, okay, that angle is 41.8. So the supplement to 41.8 would be 139.1, or around 139. Let's just say 139. Okay, 139, 138. Is that okay with everybody? Well, what do I get when I add one? So the supplement would be 138. So I'm saying this angle right here would be 138. But plus the 45, what's 138 plus 45? It's more than 180, isn't it? So because that sum is more than 180, there's no way that I could have a third angle. Okay, so there would not be a second triangle. So when we go, I'm going to show you the steps that put that logic into an organized framework for these problems. But I want you to understand why there's going to be a step, why we subtract our initial angle from 180, that's the reason. Okay. So as we go through the ambiguous case, we always got to remember that. And you guys remember me talking about yesterday when I wrote it down as the ambiguous case, I said it's a pain in the butt, right? Angle side side in that order, pain in the butt. So whenever I see that, I'm going to have to do all this work, all that logic that we just talked about. And it signifies that I got more things to do than what I would normally do on a law of sine question. Okay? If you are a person that printed out the notes, these notes are exactly what was being discussed there, but in like a static picture. Okay? Let's see here. Let's do this one. And I'm just going to cut this out and move. I think and this is kind of how I structure my upper level math courses. When I write notes, I make them very detailed to the point where if you miss something in class, you can go back to the notes and gain. I try to write them a lot like textbooks, but I think textbooks a lot of times leave things out that they make assumptions about the students, and even reading a textbook, you're still not might not be able to really get what's going on. So that's kind of why those notes are as involved as they are. But doing the example, I don't want to look at that information. I want you to do this from square one with you guys. Okay, so this is an angle side relationship. So we know that the ambiguous case is is the situation, and there's a potential for having 0, 1, or 2 solutions. Okay, it's really easy when we get 0 solutions. What will happen is that we'll write our proportions out, and we'll go to our calculator and try to solve it, and our calculator will say domain error, and that will just tell you that that's 0 solutions. I don't know that I have any examples that do that. So a lot of these are going to be either 1 or 2 solutions. So first thing we're going to do is set up our law of sines from the information that's provided. They're telling us that angle A is 20 degrees. Okay. Segment A is 20 units long. Segment B is 32. Okay. So what we're going to do is we're going to set up our proportion. We're going to say sine A over side A equals sine of B over side B equals then sine of C over side C. And that one right there isn't really, it's never going to be used in this problem because the fact that there's 2 variables there, and then mesh it with anything else, it's going to relieve 2 variables in the equation. But if I use the first 2 ratios there, that leaves me with 1 variable, right? Okay. Now, it's going to be a little bit different than what we did yesterday because of what they're asking for here. Yesterday, they asked us for a distance. So it was pretty cut and dry, cross multiply, solve for the variable, type in my calculator. Right now, we're going to cross multiply. We get 32 sine of 20 degrees equals 20 sine of B. That B is your variable, right? It's the only variable in the problem. And that's stuck inside those parentheses. You cannot do anything with that until you get sine of B by itself. So what do I need to do to both sides to get sine of B by itself? Divide by 20. Good. So I'm going to do that. And we'll get 32 sine of 20 degrees divided by 20 is equal to sine of B. Okay. Now, we're going to jog our memory a little bit back to what we first talked about, I guess, second part of 8.2 or 8.3. Now we're looking for an angle measurement. So does anybody remember how we get that B pulled out of the sine function? Now we got to use the inverse. Good. So go sine inverse of both sides here. So sine inverse here, and those are going to cancel, leaving me just B. Once you do to one side, you got to do the other side, so we get sine inverse there. Okay. Now, every single time that you get angle side, that is going to be the algebra that you first go through. Okay, so it's very, my hope is that when you did your homework yesterday, or that you look at it again tonight, that you see that a lot of the questions, whenever we're doing law of sines, they're very repetitive, doing the same thing over and over and over again. Now, it might be different numbers, but it's the same algebra, okay? No matter what I ever do with a angle side, I'm always going to have a proportion like this. I'm going to cross multiply and get something like this. The next step will be to take the sine inverse of both sides, and then I can evaluate that in my calculator. The only thing you got to pay attention to in your calculator is the mode, right? So go to degrees. So I'm going to type in sine inverse. Remember, That is the same thing as the phrase arc sine. And we'll go 32 sine of 20 divided by 20 again. Gives me 33.18. 33.18. Okay, so B, 33.18 degrees. All right, so at this point, and this is where our organization has to come into play. Okay, I am now, once I find my first angle measurement, I am going to create, basically, I try to visualize this in my work as kind of a table or chart with two sides. Okay, so the left-hand side, this is a potentially solution number 1, and this one's going to be potentially solution number 2. Okay, if there is a second solution, then the angle B for our second solution is going to be the supplement of that number right there. Does that make sense? Okay, so I'm going to take 180 minus 33.18. So this is why I like Desmos. I can actually tell B is equal to that, and then say, okay, well B supplement would be 180 minus B, 146.82. 146.82. Okay, I'm just going to put possible. We haven't decided yet whether it's actually going to be a solution or not. But that if it is, that's how we find it. Does that make sense? Okay, now we just have to decipher, is it going to be a solution? First thing I'm going to do is look at solution 1. And hopefully it makes sense that solution 1 is obviously an answer. If solution 1 had a 33.18 for angle B, and it had angle A was 20, does that leave room for angle C? Yeah, so if I go 33.18 plus 20, remove that from 180, gives me 126.82 degrees. So right now I know those 3 angle measurements for my first triangle. Okay. Now let's see if there's angle measurements for a second triangle. If I look at angle A, because in the second triangle, this angle A still had to be 20 degrees, right? If I go 20 degrees plus 146, that's 166, right? Is there room for angle C still? That make sense to everybody? Okay, so I have not exceeded that threshold of 180 with those 2 angle measurements. So I'm going to go 146.82 plus 20, subtract from 180. We get 13.18 degrees for that third angle. So this is a situation where there are indeed 2 solutions, because we have a situation now where those 3 angles can coexist in a triangle together. Is that okay with everybody? Manny? So we knew, so this was the supplement, right? We knew that one. And we knew we started with 20 because that was defined in the problem. So if I add those together, that gives me 166.82, and subtract that from 180 to give me that angle C then. So we still haven't solved the triangle though, okay? Because in order to solve the triangle, we need to find, we're missing side C here now, okay? So when I have these angles, okay, I can come back up and say, okay, I was going to rewrite this expression, this, I don't want to call it an expression, this extended proportion, but put in everything that we know now. So we know sine of 20 over 20. We know now sine of B. B is now 33.18 over 32. We know sine of C, but C now we just figured out to be 126.82, right? Over lowercase c. Does that make sense to everybody? Okay, so going through the first law of sines gains enough information for us to ultimately fill in that last ratio that we didn't know anything about. Now, if I'm going to try to find lowercase c, I better use that ratio. Okay? Now, what stinks about that is that 126.82 number, it's rounded. Okay? So I'm already going to have rounding error involved here, but I want to minimize rounding error. Which of these next two would probably be the best one to choose so that it minimizes rounding error? Yep. Okay. And now that turns into a problem just like we did yesterday, where I can take, I'm going to cross multiply, so I'll get 20 sine of 126.82 over, equal to, cross multiplied, and then C sine of 20. Divide both sides by sine of 20, right? All right, so I'll write down what C is. So we're looking at 20 sine 126.82 divided by sine of 20. $46.81. Okay. So we could have one triangle with those 6 parts. Parts to start us off with. And those highlighted parts. Okay. Now the second triangle, do the same thing. Now we would know sine of 20 over 20 still. Okay. But now, in the second triangle, angle B is that. So now it would be sine of 146.82 over B, okay, which we knew B was 32, is equal then to sine of 13.18 over C. Again, to minimize rounding error, probably want to use those two together. And now, cross multiply, I get 20 sine of 13.18. And then C times sine of 20. Divide both sides by sine of 20. And let's see what C gives us. And a lot you'll find out, and this is what I don't like to teach it this way, but you'll find out as you do enough examples of this. Once I did all the work on the solution 1 over here on the left, okay, the exact same work, whether I want to do it by hand or not, is the same thing that's going to happen on the right. And if you noticed, so this was the work that we found C on the left, right? Well, the only thing that changes instead of 126.82 is now we use what we thought C to be here is 13.18. That's really the only thing that changes. So if you can remember that, or you can use that, 13.33 then would be that triangle. So those are our two solutions. We have a triangle that could have angle A to be 20 degrees, angle B to be 33.18 degrees, and angle C to be 126.82 degrees. Segment A would have been 20, segment B would have been 32, and those were given, and we would have found then segment C would be 46.81. Or we could have a triangle that has angle A to be 20 degrees, angle B then to be 146.82 degrees, and angle C to be 13.18 degrees. That would have been making side A being 20, side B being 32, and those were given. And then side C we just found to be 13.33. And those would be then the two solutions that you report. Now, go back to my first statement. Angle side is a pain in the butt, right? Okay. My hopes are you could see that yesterday we probably did 3 problems yesterday in the time that we did 1 here. Okay. Angle side is always going to throw you a little bit of a curveball. Okay. Now, if we would have gotten to the point where this third angle would not have existed, so let's say that we found this B here to be like 166. And when I add 20 to it, I get 186, so there's no room for C. Then I say, okay, I only got one solution, and I go through and I work that one solution and report that one solution. Okay? But this is what we're talking about. So I want to show you, it might take a minute to construct this, but I'm going to show you this exact scenario in GeoGebra. But give me a minute. I'm going to pause. Okay, so this one is, so this triangle on the left is maybe the one that we start with. Okay, and we go through, and the angle that we first came up with for C, or not C, B, which would be the 33.18. Okay, so that's going to end up being, when I come down here and I look at this angle right there, okay, that's pretty close to 33.18. You guys agree with that? Okay, so it's showing that when I connect there, I do get 33.18. So then over here on this one, closest as I can, zoom in. Okay, 146.76. So what was the value that we came up with? 146.82. So pretty close. Okay. Now they would equate. Obviously, if I zoom in, you guys can see far enough. I'm really not on that line, right? So let's see if we can make it better. And there, we made it better. Okay. So there we see the supplements of those things, right? Okay. So now the remaining distances, so the distance of the third side that we are interested using the law signs to find would be from that side. So that little lowercase c that we found would be that point to that point, 46.81. Did we find a value of 46.81? Okay. And then the other one would have been this distance from there to there, which was 13.33. And that's exactly what we found using the law of sines. Okay. So when we were provided that initial information, okay, and this picture here is kind of eliciting probably the yellow picture, okay? But there is a second triangle that can and does exist with those dimensions, okay? I think it's one of the harder concepts to initially understand in geometry, but what's awesome, we're going to spend too much more time on that, but what I've noticed in the past is that explaining that to you at this stage, you'll go maybe use it in a science class at some point and be explained again. But when you guys come back to me in trigonometry, for whatever reason, I don't know if it's because we're more mature, we're a little bit older, okay, 2 years older, students understand that so much better when we get back to trig, okay? And in the past, when I haven't shown it in geometry and we get to trig, it's fuzzy. But seeing it now and then in a year and a half, come back to it, it will be something that you guys fully understand. Okay, I promise. But that is the law of sines. So A lot of times in actual practice, we don't use, we're using the law of sines to help us find unknown distances. A lot of times the ambiguous case does not take hold in like real life scenarios. Okay, could, but usually doesn't from the problems that we are provided. Okay? So that is the law of sines, ambiguous case. So let's try this one real quick. Here we're saying that, again, using the law of sines, we'll put angle A to be 20 degrees. B is 14. A is 8. So again, this is an angle followed by a side, followed by a side. So this is the ambiguous case. So we could have 0, 1, or 2 solutions. Okay. If I start setting things up, I'm going to go sine of A over A equals sine of B over B equals sine of C over C. So that's sine of 20 over 8. Sine of B over 14. And sine of C over C. So we're going to use those two, correct? Okay. Now, just like the last one we did, once we choose those two, and we know it's the angle side, it's the ambiguous case, then when I cross multiply, the algebra, what I'm trying to say is the algebra is identical to what we've already done. So if you can do one of these, you have a template in front of you from the first one we did. You copy that template and that procedure every single time. So I'm going to cross multiply. I'll get 14 sine of 20. I'm going to multiply my extremes. Multiply by means, I'm going to get 8 sine of B. Okay? What did we do in the last one when we had this phrase here? Divide by 8. Give me 14 sine of 20 all over 8 is equal to then sine of B. Then what was the next thing you did? Take the inverse. So I go sine inverse of the right-hand side and sine inverse of the left-hand side. And those cancel. B equals, ultimately, that thing right there. I don't want to rewrite it. Okay? Now, here's the thing. Remember, and we can type this in our calculator, and it'll validate what our calculator does or tells us. Sine of 20 is like it's less than a half. Okay, it's probably around like 0.3-ish, 0.4-ish. But whatever. So that number times 14. Okay, and then divided by 8. So what's going to happen here is when I evaluate this, that number, let's just see what the number equates to real quick. Sine of 20 is that. Okay. 14 is that. Divided by 8 is that, right? Okay. If I go sine inverse, we get that number there, correct? Okay. Now, if I take that number right there, okay, which is the first angle, so we know we have that angle, so I'm just going to call that, what is that, B? I'm going to take the angle A, which was 20, okay? If I take 180 minus A minus B, I think I got B listed several times here, so let's get rid of those. Okay, we get 123 degrees for our third angle. That would be angle C. Does that make sense, everybody? So right now, we could have those three angles in our triangle. Okay, so that would be one solution. Angle A is 20, B could be 36.7, and C could be 123.23. Okay, now that was solution number one, and this was the first angle that we found. So if there is a solution number two, then B, that angle right there, we know angle A has to be 20. That was defined. That was given. Then B has to be the what compared to that? It has to be the supplement of that 36, doesn't it? So what is the supplement of 36? Be 180 minus B, which is that number right there, right? Okay, 143. Do we have enough room now for angle C? That make sense? Okay. Angle C then would be, it's got 143. Plus 20. So angle C would be 17 degrees. Okay, so that's another situation where we could have two solutions. All right. Let's look at, let's see here. This here, this statement should have a different image with it. Let's go. Say we put 20 there. I want this number to be 8. Let's try this. This will work. Okay. Let's just something like that. Okay, and I asked you, can you find, because this is the angle side again, can you find angle B? So we would go sine of 20 over 4 equals sine of B over 28, right? Is everybody okay with that? Okay. When I cross multiply, 28 sine of 20 equals 4 sine of B. Divide both sides by 4, correct? Okay. And then take the inverse of both sides, correct? And that will just give me eventually B. Now, what's 28 divided by 4? 7. So I'm going to go sine inverse. And you can just grab your calculator, type this in, but I'm just going to try to prove a point here. We saw that 20, sine of 20 earlier was like 0.34 or something like that. If I take 7 and multiply it by 0.34, okay, that's a number bigger than 1, okay? So it's about, it'd probably be about 2.1-ish, 2.2-ish, something like that, okay, in that ballpark. If we remember what is going in, what is this thing, when we go in the sine inverse, we're spitting out the output, it's a function, and the output is an angle, right? The input, remember, is a ratio. And because it's the sine, it's the ratio of opposite divided by hypotenuse. In any right triangle, the hypotenuse is the what of any right triangle. What side, how does it compare to the other sides? It's the longest. So if I take a number divided by something that is always bigger than it, I should always get something that is between 0 and 1, correct? Okay. Well, here, so I should never be able to put any number in here other than something between 0 and 1. Okay. If we go back through all these examples, that number right there ended up being between 0 and 1. All of these examples above, every time we've ever done sine inverse, the input has been between 0 and 1. Okay. Well, if I do this now with the sine inverse of 28 sine of 20 divided by 4, you see how it says it's undefined? Because we're putting in 7 sine of 20, which is that number right there, 2.39. That is being put in as an opposite side divided by a hypotenuse, and that is impossible to happen. That kind of makes sense? So when you get that from your calculator, it says undefined, you have no solutions. Okay? That would be the situation where you have no answers. And if I have no answers, let's look at what it means graphically to us. If I have 20 degrees, what do we say? One of those sides was 28. And this side would have been 4. Okay? Do you see why there's no solution? Does that little segment ever touch this third side? No. So that's I told you guys I was going to show you the physics of the angle side. This GeoGebra here is the physics showing us, okay, why does my calculator say undefined, and then why do I then say, well, that's no solutions? It's because of what's going on with the actual image here. We cannot physically create a triangle with those dimensions. Is that right with everybody?